Yeah, it is our pleasure to have today at our seminar, AI seminar at TI, Professor Samson Lasaulce. What is the right pronunciation? Samson?
Yes, Lasaulce.
Lasaulce, great. Yeah, and Professor Lasaulce, he's a Director of Research at CNRS, and his research interests lie in distributed networks with focus on game theory, optimal control, distributed optimization, energy network, social network, and now climate change, which is a very important topic as well. And we recently had a talk on this topic at our seminar. So I think that it's the right time to start. And Professor Lasaulce, the floor is yours, please.
Okay, thank you, Maxime. So I would like to thank all the organizers for inviting me today. So I'm going to share my screen now. So we are going to talk about quantization. So when I received the invitation, I didn't know it was for more like AI team. So in fact, I'm not going to talk about learning, machine learning today, but the problem we are going to see together, in fact, you can apply many machine learning techniques for this problem. So I will talk more about this at the end of the talk, okay? So maybe you will see by yourself where you can apply machine learning. Okay, so we are going to talk about quantization since probably some of you have different backgrounds. I'm going to review quite briefly what quantization is, okay? And then we'll go into the details. So, by the way, this presentation is based on a couple of papers, okay? Some of them are still under review, but it's not a problem, I can give them to you. So the references, the background, the precise background can be found in these works, okay? So I'm not going to give you all the details about this. And then same thing, technical details for algorithms, proofs, you can find in the paper. So the goal of this presentation is more to see what are the problems we have addressed and what are the results, what is the performance of what we did. Okay, let us start. So quantization is defined like this. So you take a space, okay, and it is a subset of Rn, okay? N is a dimension of the space parameter you consider. And then you have an integer m, okay? And what we call quantization is, in fact, when you partition this space into subsets, okay? So you have m subsets, capital M subsets. So you partition into several parts, okay? So the union of the subsets give you the space. And of course, there is no intersection between two subsets. Okay, that's the definition of a partition. So you partition any space you want. Here it's continuous, okay? For this presentation, everything is going to be continuous. And then we switch to the discrete case. We'll talk about this later. And for each part here, each subset has a representative. So you have a mapping between each part of the space and a given point of the space, okay? So if you represent this in a geometric way, you have this, okay? So you have your space here, could be G, okay? That would be G, okay, this guy, okay? Then you partition G into several subsets. Here it's called calligraphic C, sorry, but it should be calligraphic G. And each subset has a representative Zm, okay? So that's what we call quantization. So it's a purely mathematical operation. So this mathematical operation can be represented by a function, okay, an endomorphism, okay, and for each point you associate a certain representative. So in fact, Q, a quantization function, is just a piecewise function, okay, which is defined like this. Okay, so that's the definition, and it allows us to fix the notations. Is it okay so far? Don't hesitate to ask questions during the talk. I think it's better than being lost by notation sometimes. Okay, so that's the definition of quantization. So now the question is, of course, when you want to quantize some quantities, okay, the question is, how do you choose these subsets G, and how do you choose the representatives? Okay, that's the technical questions. So the conventional paradigm, okay, for quantization is in fact essentially to minimize a distance between G, okay, the input, and its approximate. Okay, that's the conventional paradigm. So essentially, you care about accuracy. And one very well-known accuracy measure is what we call a distortion. Okay, so that's the Euclidean distance between G and its approximates Q of G, and here it's average over the distribution of G. Okay, that's what we call the most conventional quantization paradigm. So we care about reliability or distortion. Okay, good. So if you apply this paradigm, for instance, to compress an image, so you have this image, for instance, you want to compress it. So what is going to happen? So you have an original image, you take a picture, you have something like that, 10 to the 7 bits, okay? And then you compress it, and you are going to compress it so that you have a sufficient quality, so that allows you to go to 10 to the 6 bits or 10 to the 5 bits, okay? Essentially, this is how classical compression works, okay? So you decrease the size of the image so that the distortion is small or cannot be seen by the user. Okay, that's the conventional paradigm. Okay, good. So now assume, in fact, that the user is not interested in the accuracy of the compressed image. Okay, and in fact, let's consider a simple situation when what the end user wants is just to know if there is a ball or not in the image. Assume this is the task of the user. It might be a machine or human, but whatever, we don't care. But this is what the end user wants, just to know if there is a ball. So if you think about that, if this is what the end user wants, you just need to send one bit and to say, okay, there is a ball or there is no ball in the image. Okay, so that's the thing. If you use the conventional data compression algorithms, okay, in fact, you send too much information because you don't consider the final use of the content, okay? And as you see, you can compress and get something like 1 bit per image, which means you have a huge compression ratio by considering the final use. So this is the approach that we have considered for this quantization problem. Okay, so the idea is that, okay, you know the task, you know the final task, you know everything about the final task, and how can you tailor the quantizer to the final task? That was the initial motivation for this work. Is it clear to everyone? It's okay? Yes? Okay, so that's the idea of goal-oriented quantization. So why do we consider the problem of quantization? Okay, because you say, okay, essentially we could directly consider goal-oriented communication. Okay, so here we are more modest and we just consider quantization, and here are some motivations. So first of all, quantization appears in many practical situations. Okay, every time that you want to convert an analog signal to a digital signal, so say when you have sensors, analog measurements for the Internet of Things, or in many situations, okay? And we know about this. So first of all, quantization is very important, okay? And the second thing is that if you want to design a goal-oriented source coder, okay, it's important to know about quantization, because it's like a first brick of a lossy source coder, okay? So this is what you have in JPEG, this is what you have in many data compression, device or algorithm. Okay, so that's the second motivation. If you know about quantization, then you will know more about this general setup. And another motivation is that, in fact, data clustering, okay, or data classification can be seen as a quantization problem. Okay, so in fact, this is what we are going to show a bit later. And goal-oriented data clustering is also very useful now in modern applications. So these are our motivations. Okay, so now how do we define goal-oriented quantization? You're probably aware that now there are more and more papers on goal-oriented communications, semantic communications, okay? But when you look at all these papers, you will see that essentially either there is no formal definition, okay? It's more like conceptual things, but there is no mathematical definition of goal-oriented communications. That's one possibility. Or you will find some very specific set definitions which work for the problem at hand. So in fact, what we did is like this. We use a quite general definition, okay, like defining a class, if you want, of tasks to be executed, but at least the formulation is general. And the definition that we are going to adopt today for goal-oriented quantization can be found in this paper, okay, that we wrote in 2018. Sorry, 17. Okay, so what is definition? So the definition is like this. So you take your task, okay, whatever task you want, but the condition to apply the machinery we are going to see together is that you can model your task by an optimization problem. Okay, this is how we model a task. It is an OP. So if it is an OP, there is an objective function to be, say, minimized, okay? And then you can also put some constraint functions, okay? Of course. And the goal is this. So you represent your task by an OP. And then you look at your objective function and you partition your variables, okay? And you define two types of variables. First type of variables is called decision variables. And the second type of variables are called parameters because you cannot control them. Yes? So how is it related to quantization now? It is related to quantization because what we assume is that, okay, you would like to minimize this function, okay? But you don't know G. Okay, you want to minimize this function with respect to X, the decision X, but you don't know G. You only have a quantized version of G. Okay, and the goal here is in fact to minimize this function under this imperfect but structured knowledge of G. Okay, so a simple example in wireless communication would be that X is a power allocation vector, say for, I don't know, you have massive MIMO, you want to allocate your power between many antennas, so you have to choose this power allocation vector, and the knowledge you have is a quantized version of the CSI, the channel state information. So that could be an example of this type of problems, okay? But it's more general, in fact, okay? Okay, so this is how we define goal-oriented quantization. Now, the goal is to find, of course, a good quantizer. So for this, we are going to make assumptions. Of course, all the assumptions are detailed in our papers, so I will just mention some of them. But for the analysis, not necessarily for the design, but for the analysis, we assume that you have access to the optimal decision function. Okay, so you want to minimize this function, and we call this chi of g the optimal decision. Okay, so you can take another decision, not necessarily optimal, and then you would need to revisit just a bit what we did, not much, but at least what we did is for the optimal decision. Okay, but they can be extended. So what is the goal now? As we said, ideally you would like to minimize f. Okay, so if you minimize f and you know g, okay, you will achieve this value. Okay, because this is the optimal decision here. Okay, so if you know g, you achieve this. But since you don't know g and you have only access to the quantized version of g, okay, you will achieve this quantity. Okay, so there is a loss of optimality which is induced by the fact that you don't have access to g, but you have only access to q of g. And what is the mathematical objective now? The goal is to minimize the average of this loss that we call the optimality loss. Okay, the optimality loss induced by the quantized knowledge of the parameter. And this gives us the performance metric that we consider. Okay, so it is a functional, of course, okay, because Q is a function. Okay, so L is a functional, and it is parameterized by the function you consider, and it is an average of this, the expected version of this, since phi is in fact the distribution, is the PDF of G. Okay, and then here I don't want to spend too much time on that. This is a normalization factor. Okay, we don't need to talk about this now. So this is how we define goal-oriented quantization. That's our objective, and we want to minimize this functional with respect to Q. Okay, and then the obtained quantizer will be called goal-oriented for this reason, because the goal is F, and you want to have the better value you can have for F given the knowledge you have. So how do we do that? So it's not easy in general, because in fact, this problem generalizes the classical vector quantization. Okay, so for the classical vector quantization, what do we have? You have f g, which equals x of g. Okay, this is what we have for classical quantization. So, of course, all the difficulties you have for classical quantizations, you will find them for the generalized version we have here. Okay, so in general, it is not that easy to minimize this function. Okay, so you're going to resort to tricks to proceed. So the two questions we would like to ask, or to provide some elements of answers, are those. First, how do we find a good quantizer, okay, to minimize this optimality loss? And then there is a second very interesting question, is that, okay, are there some classes of goal functions for which the quantization operation is harder or easier? Okay, so if you want to understand what we are talking about here, is think about when you compress an image. For instance, you know, if you have an image and you don't have, say, you have a low frequency content occur, then you know it's easier to compress the image with some JPEG compression. Okay, so depending on the type of image, you know this image is easy to compress, or if you have now some text, then you have a lot of high frequencies. It's more complicated to compress by using some JPEG. Okay, that's the idea. The idea is to see, okay, I consider a function which represents my task, but are there some tasks for which they require more, say, more information about the source or not? Can I classify this problem? Okay, so first one first approach to move is in fact to consider this case. First, we consider the scalar case. Okay, that means the dimension of the space is 1, and then we assume that the number of regions or intervals in this case is going to be large. Okay, so what I mean by large again is very well defined in the papers, but for the presentation I just going to be say informal. So that's the setup for this high realization scalar quantization. So the function is fixed, the goal function is fixed, n equals 1, m is large, this is what you said. And then we call delta of g the quantization interval, okay, around g, okay. And we define this density function, okay, which is in fact the interval density function, okay. Rho of g is 1 divided by m, the number of intervals, quantization intervals, times the quantization step. So this function tells you, if you want, how many intervals you have, subintervals or quantization steps you have for some interval of your space. Okay, it tells you how dense is the quantization process. Okay, this is what. So if you determine this in the high resolution case, then the problem is solved, because if you know the intervals, then you know the representatives, because in the high resolution regimes, the best representatives are taken in the middle of the intervals for smooth functions. So if you determine this, then the problem is solved. Okay, and then you will know where you, if you want allocate your bit budget, I would say, okay, for this value of g, I will use some very small intervals, and for this value of g, I will use large quantization intervals. It will tell you that. Okay, this is the information you have. So what we have proved is this. We have proved that the best interval density, okay, function is given by this. Okay, is given by this, and you obtain this in the high resolution regime. And let me comment this. And in fact, you're going to see it is a particular case. I agree with that, but you can extract some very useful informations for the general case. What do I mean by general case? I mean either for the vector case, but also for the low resolution case. Okay, so let's talk about this now a bit. So the best density is given by this formula. So again, C is just a normalization factor. Let's forget about this. And this is what we have. So first, the density of quantization intervals, okay, is related to the density of the parameter. Okay, so for instance, if G is assume G represents Rayleigh fading, so that phi of G would be an exponential. Okay, so that's the classical result. When you want to minimize distortion, that means you consider this function. When you want to minimize distortion, the known result is that the optimal density is related only to phi. Okay, and in fact, for the it's 5 to 1 to the 3 for people who are familiar with this. This is the classical results. So the classical results say, look at the density of the parameter, the distribution, and then you build your quantization interval based on that. And the problem is solved. So we see here the situation is more complicated because the way you should allocate your bits, your quantization bits to the value of G, in fact, it depends on the regularity properties of the goal function and the decision function. So implicitly here, we have assumed that these functions are, of course, differentiable. So they are smooth, okay? We assume everything is smooth. And what you prove is that the optimal density is related to a certain power, okay? A certain power that we call kappa of the first derivative of the decision function and the kth derivative of the goal function. So that tells you exactly how you should, say, allocate your quantization bits for the different value of G. So what is this kappa? This kappa, it comes from the Taylor expansion that we do for the high resolution approximation. And this kappa is, in fact, the mean of the minimum index such that the derivative of f with respect to the decision is non-zero. That's the kappa. Okay, so you can find all the details in the thesis of Heng Zhu or in the recent paper that we have revised. Okay, so that's a very interesting result. So, of course, the question is, how do we exploit it? So let's see how to exploit this result for a simple example, okay? Let's consider this example. Assume your goal function is this function, okay? So you take C is a constant, X is a decision variable, G is the parameter, and here at the denominator, you have X to the eta. So if you have this goal function, and you would like to minimize the average or the expected optimality loss, when the density of G represents a Rayleigh fading, okay? So you have an exponential law, okay, for G. This is what you get. You get that the optimal density for the quantization intervals is given by this formula. Okay, good, we have this formula. So what does it tell? In fact, if you look at this density, okay, okay, I don't know the exact shape, I have to look at this, but anyway, the shape would be that it is like this. There is a maximum, rho as a maximum in G bar, okay? G bar is the expectation of G. So what you see is this: the density is going to evolve according against G according to this law. So what you see is that this result is different from the classical or conventional quantization. Why? For conventional quantization, you know that rho is directly related to phi. So that means if a certain G has more probability, then you give more bits, then you allocate more bits, okay? This is what you have. So that would be the classical approach. But here you see it's not the case. The place where you allocate the largest number of bits is around the mean of G bar, okay? So you see that changes the way you allocate the bits. So you would say, okay, how can I use that, say, in other situations? So this insight, in fact, is quite powerful. Think about, for instance, lossless source coding. If you think about lossless source coding like arithmetic coding, Huffman coding, and all of this, if you think about this, how does it work? It thinks you give, you map long code works, okay, to events which are the most likely. Is that this is what you would do with this classical approach. But what you see is that this approach is independent of the goal. So you could revisit this lossless source coding based on this type of insights, which tells you how you should look at the probabilities of the different events of the source and use this knowledge to adapt the length of the code words. Okay, so this is the type of insights that you can extract from this approach. So essentially, you revisit completely the problem of lossless source coding based on these observations.
Excuse me, Samson, I have a question.
Yes.
The question is it obvious that the maximum is in G bar? Because I see that G bar is a characteristic of phi, while you multiply it by G in some power, which is independent of phi. So it's not obvious for me that maximum is in G bar.
To be honest, I have not checked. Okay, my student did it, but it should be right. Yes, it should be right, because you have this result, but I can check if you want. But yes, in fact, this is because you have this G. Okay. And we assume that eta equals 3, okay? If you assume equals 2, then you find the classical result, okay? You agree? Because then the dependency of G disappears. Yep. But since you have a dependency on G here, and the function is increasing, and you multiply by a decreasing function, okay, it is exponential, so you have this kind of behavior, okay?
Okay, thank you.
And then the exact value should be G bar. I have not checked, but it is like this. The shape is for sure like this, but then the value is G bar, and you can check that. Yeah. Okay. So now we are going to talk about a second problem. So remember, say, okay, can we find a good quantizer? So here we just provided some elements of answers. So let's provide some elements of answer to this problem, okay? To say, okay, are there some function for which quantization is more difficult, or some task for which the amount of information should be higher, if you want? So let's consider these two functions, okay? They are very popular in the wireless resource allocation literature, okay? So this function could be represent an energy efficient metric, and this represents the spectral efficiency of a certain system. Okay, so let's consider those two functions. Okay, so again, in wireless, X could be some, say, again, power allocation vector, and G the CSI. Okay, to make it simple. So, and this function represents the packet success rate, and this represents the transmission cost. This is what we have. Okay, good. So we consider these two functions now. And the question we ask, is there a function which is easier to compress or not? I mean, is there a function which is more sensitive to quantization noise, if you want? That would be the question. Okay. And in fact, if you consider now the optimality loss that we have considered before, okay, it's just that here we consider in percentage, so we just normalize by the maximum value you can get in the perfect case, okay. And if you plot this quantity, okay, by using Monte Carlo simulations, okay, that's the optimality loss versus the number of quantization bits to quantize the G, okay? So you quantize the GI, and then you perform the optimization of these functions, okay? And you look at the optimality loss in the sense we have defined before. And what happens? What you see is that for, say, 5 bits per sample, okay, for every GI, you see okay, the optimality loss is small for both functions, both for energy efficiency, both for spectral efficiency. But now, when you decrease the number of bits, okay, say let's go for 2 bits per sample, what you see is that the energy efficiency functions is very sensitive to quantization noise, and the log function is not. Okay, so this is what we mean by this notion of hardness to compress. Okay, we are saying that for some task, okay, it's easier to compress the G, and this will have no effect, but for other situations, it will have a big effect. So essentially, conclusion would be that energy efficient function here is harder to compress than this function. That would be the conclusion based from these purely numerical results. Okay, so we said, okay, we have observed this. Now can we prove something? And in fact, this problem is not trivial at all. It's not trivial at all, and it is a mathematical problem which requires some energy. So we have tried to produce some results. Okay, and in fact, what we can do is that for the scalar, the high resolution scalar quantization, you can give some results, and this is what we did. So we did this for many functions. So you can look at different goal functions, okay, log, exponential, quadratic, etc. Then you consider different, if you want, PDFs. You get the optimal decisions, and then you look at the optimality loss. But the optimality loss, I insist here, it's not obtained from Monte Carlo simulations. It can be computed because everything can be calculated, okay? So you have the value. So that means the optimality loss in the high resolution scalar case can be obtained without Monte Carlo simulations. And what you have is this. By consider the OL, okay, with a certain normalization factor, you have, in fact, a certain value for the optimality loss, and you are able, in fact, to compare the functions. Because you see, for instance, for the log function here, minus x, you see that the optimality value, the OL, is very small. And then here, when you look at the exponential, is higher. Okay? So in fact, what it shows you, it tells you, okay, you have a function that you would use for the vector case with low resolution. Now, what you can do is use the same function in the high resolution scalar case, and then you can have an idea about how hard is it to compress, because you can compute exactly, in fact, the value of the optimality loss in this regime. Okay, and in fact, we can in fact predict this from this type of tables. We don't need Monte Carlo simulations. And then when you perform a Monte Carlo simulation for the vector case, you will find the same hierarchy between these functions. Okay. So all these results would need to be proved, and it's not trivial, but we have at least observed them. And it is very interesting because a very, very solid work would be to define some classes of functions, and then you would be able to say, okay, this function difficult to compress, this function is not. Here it's more like about like a statement or observation, or like a first step into this difficult and interesting problem. Okay, so let's talk about the vector case. So the vector case is trickier, definitely, is trickier. And I'm not going to give you the equations because it takes too much time for a presentation, especially remotely. So you can find them in those references, okay? Here, okay, just ask me, I will send you those references and you will find the details. Okay, so for the vector case, just to summarize with some text about what we did. So for the vector case, we also consider the high resolution regime. okay? And then what comes up, in fact, what appears is this matrix, okay? We have a matrix which has a key row. What is this matrix? This matrix is a Jacobian, okay, of the decision function and the Asian of the goal function. Okay, these are the important matrices for this problem. So if you are able to know something, either you know this matrix perfectly, or you know things about this matrix, even if you don't know the matrix, for instance, if you know the distribution of the eigenvalues of this matrix, this is useful. And this will help you to design a good vector quantizer. Okay, so this is what we have proved, that this matrix has a key row. And then we have derived some lower and upper bounds for the optimality loss by using Gershaw conjecture, okay, for Voronoi tessellation. So we did that. And then by using this, this matrix that we have obtained in the large M regime, if you want, we have been able to derive an algorithm, okay? So the algorithm we used, okay, clearly use the knowledge of F, of chi, and phi, okay? So that's one step, okay, into this direction to have a vector goal-oriented quantization. But of course, here there is a lot of space for learning, machine learning, okay? Why is it some space? And in fact, this will be part of my conclusion, because if you relax one of them here, the knowledge of one of them, then you can use machine learning and try to compensate for this loss of knowledge as much as you can. Okay, so this is what we did for vector quantization. Then I'm going to present some numerical results to illustrate and to show how it works. So let's illustrate, let's provide some results for the vector case. So let's consider, we have considered some log functions or exponential. Let's consider other type of functions, like this quadratic function. This would be relevant in control theory problem, for instance, okay? Let's consider this quadratic function, okay? And the dependency to G is given here. So if you consider this function, for instance, and you look at the relative optimality loss, yes, versus the number of quantization regions or cells, yes, this is the type of performance you can get, the typical performance you can get. So this is the optimality loss in percentage that you would obtain by using Loimax, say, or distortion-based vector quantization, okay, the black curve. This is what you would get. Then if you use our approach, this is what you would get. You would get, say, for only 5 quantization regions, okay? So you see, in fact, we are not working in the high resolution case because we have only 5 regions, okay? Even for 5 regions with the algorithm we propose, you have relative optimality loss, which is 10%, which is much better than the conventional quantization paradigm, much better, okay? Even if you have an approximation that is obtained in high resolution regime. You see, this is not really high resolution regime. It is probably around this area, but not here. And it still works. This is what is interesting, okay? Again, it's just like, I know at TI, some experts, there are some experts about the random matrix theory, okay? So I don't have the analytical arguments for that, but there should be some arguments to explain why it works so well, even if the number of regions is small. Okay, so we will need to comment on this observation, but at least you see, for this type of functions, dimension 2, it works very well. Of course, if you increase the dimension here, and the dimension would be like 100, then you would probably need to revisit this observation, but it needs to be done to understand this problem. And then just for comparison, we have considered a quite recent work by Yonina Eldar, and you see it was quite advanced, okay, and quite close to this goal-oriented approach, and still we beat their algorithms quite significantly. Okay, now if you want to understand where the improvements come from, okay, and this is the same story as we did for this simple example. Remember the example with this function that we have proved that we have a maximum at G bar. So this is the density of the parameters. This is an exponential density for the parameters. So that would mean with the classical approach, you will follow this density for the quantization intervals in dimension 2, okay? So same observation as before, but for dimension 2. Now, if you look at the density we obtain with our algorithm, it's like this, okay? And why is like this? In fact, because what the algorithm does is this. It takes this density. So this density is phi, okay? And in fact, it applies a transformation on phi, okay? It applies a transformation on phi. And the transformation that we apply on phi is based on what? In fact, it exploits the eigenvalues of this matrix. So by knowing the eigenvalues of this matrix, you can apply a transformation on the original density, parameter density, and you obtain this, this shape. And in fact, this is the right density to be considered for the bit allocation problem that you can have in a vector case. Okay, this is what we do. Okay, so these were some results for the vector case, but so far everything was continuous. Okay, those guys, they were continuous all the time. Everything was continuous. Okay, okay, good. And the other thing is that we have assumed that so far that phi is known. So now we are going to consider another setting, which is goal-oriented data clustering. And for clustering, you don't have, typically you don't have phi. You can have phi also, of course, but typically for clustering, you have a database. Okay, you have a database, okay, you have this. And so most of the time you don't know phi, maybe it's not defined, if it isn't stationary, whatever. But you have this thing, and then what can you do with the database? How can you build a goal-oriented cluster algorithm based on the database? And this is what we do. So for data clustering, it's just like quantization, okay? So the difference, where are the differences? Instead of having a continuous space G, here you have a database, okay, with n, capital N samples. Then you're going to partition this database, okay, into classes, okay, if you want, into clusters, and of course, no intersection between the clusters. So this is a difference between the quantization problem we have seen before and the clustering in the sense we are considering here. And then what do you want? You want to find a clustering function. So we don't call it Q here. You can call it Q if you want, but here you call it gamma to put the emphasis on the fact that we're working on a database. Okay. So, and we want to find a good clustering scheme, okay, in a sense of a goal. Okay, so this is what we do now. So that's the main difference with before. No phi, sorry, no phi. And then you have this databases or database, whatever. You have that. That's the difference. But still, it doesn't change much. Okay, so I don't know if some of you are familiar with this, but what we call Lloyd-Max algorithm for quantization is called k-means for clustering. Okay, so those problems are strongly related, and this is this relationship that we exploit here. Okay, so we are still interested in minimizing this optimality loss, okay, but this time we want to find a good clustering function, okay, and in fact we have simplified here the problem because for the clustering problem we have studied, we have not looked at the impact of f of the, if you want, the hardness to cluster. We have not looked at this. So for this reason, we have simplified optimality loss like this, because if you look at this, only this term depends on gamma. Okay, this term doesn't depend on gamma. So for the optimality loss, we consider this metric. Okay, directly. We have removed this term because it doesn't depend on gamma, and we don't study the impact of f. So we remove this term, and we have only this term left. And since we don't know the expectation, the statistical expectation, we consider the empirical mean of this quantity. Okay, of course, mean over the databases. All the GN are samples of the database. And that's the new, if you want, performance metric that we consider. And the goal is to maximize this with respect to gamma, the clustering algorithm or clustering scheme. And this is what we did. This is what we did. In fact, we apply this for smart grid problems. Okay, for smart grid problems, they don't have the same performance metric typically. So we consider another performance metric. Okay, which is like this. So the performance metric is the LP norm. Okay, is the LP norm of a weighting matrix times the decision. Okay, this is a decision vector, and this is the parameter, okay, which is going to be cluster. So you have to take a decision, okay, to choose an X given a cluster version of the parameter. So I can give a simple example. You have a smart meter, okay. The smart meter monitors the non-flexible power in your place, okay. What is not flexible, it monitors that. Then it sends a cluster version of this to the network. And then the network decides about the flexible power. What would be the flexible power? Could be, for instance, the electrical vehicle. So you want to find the best way of charging an electrical vehicle based on the cluster knowledge of the consumptions which are not related to the electrical vehicle. Okay, that would be the problem we want to solve. So you want to minimize this function, subject some constraints, and then you want to find the best way of clustering the information for this goal function. So this can be found in this paper. So if you do that, in fact, so by using the machinery we have presented, and then you look at the optimality loss for the LP norm versus the number of clusters, this is what you have. So we have considered many clustering schemes, the best clustering scheme we have found in the literature, and you have compared to our scheme, which is called here DMOC because it's decision-making oriented. In fact, here what I call by DMOC is in fact goal-oriented clustering. Okay. And again, there is a significant improvement by using our approach compared to what exists. So again, it shows you the benefit that you can gain by tailoring exactly the way you cluster data to the goal. Okay. Okay, so this is the type of results that you can have. Now, if you want to illustrate, so here I consider 2D because we did it for higher dimension, but 2D is just to be able to illustrate. So if you cluster the data by using the k-means algorithm, this is k-means, okay. If you use the k-means clustering, okay, this is how the k-means would cluster the data, okay. So these are essentially the counterpart, the discrete counterpart of the Voronoi regions, okay. So now if you use our approach, which is based directly on LP norm, you see the shape of the regions they don't look like Voronoi regions, they look like something else which is tailored to, again, to the function here. Okay, here you want essentially to minimize the peak power when P is large. When P is large, okay, minimizing this norm amounts to minimizing the peak power. Okay, so this is what you can get because this simulation is obtained for large P. Okay, large P that gives you then the max power. Another interesting simulation, okay, is when you look at the number of clusters, okay, you need to achieve a certain optimality loss. So here you fix a target of the optimality loss at 5%, and then you look at the number of bits, if you want, or the number of clusters you need to achieve this target. And when you do this for the LP norm, and you play with this P, okay, this is what you are, this is here the x-axis, okay, you play with this P. And when you compare the performance of the k-means algorithm with our algorithm, you see that, again, this difference is quite large. For instance, if P equals 20, you see here you need something like, I don't know, 80 clusters, and here you only need 8 clusters. So that makes a big difference. And having a small number of clusters is very useful for many things. As you know, it is useful for complexity, it is useful for interpretations, for many things. So what we show is that, again, by knowing this F and tailoring the prem to F, you can decreasing this M. And another simulation, which is very impressive, in fact, okay, this is why I show it. So this represents, in fact, the peak power you allow for your problem. So this is, for instance, in your place, okay, at home, and you don't want the peak power to exceed this. And then when you look at the required number of clusters, okay, to achieve a certain optimality loss, this is what we have. And it is very impressive because when you use k-means clustering, you see, for instance, for this peak power, you need 120 clusters, okay? And for the goal-oriented cluster, you just need something like 4. You just need 4 clusters to achieve the same performance. So you decrease the number of clusters from 120 to 4, which is quite impressive, okay? It is quite impressive because in this, for this simulation, we took P again large. That means the LP norm becomes a max. Okay. This is one of the reasons, but it shows you that there are some metrics which gives you large performance gains. Okay. Compared to a classical approach where you just cluster the data based on exogenous indices like the silhouette indices, for instance, silhouette index, for instance, and this is not tailored at all to the final objective. Okay, so that would be what I have to say for this works. Okay, and then if you allow me, I would like to conclude this presentation. Okay. So the main conclusion is about the information knowledge, because it's true what essentially, if you want, okay, we have interesting results, okay, but now what are the weaknesses, okay, if you want. The weaknesses is that for the analysis and also for most of algorithms we have derived, we assume that this triple is known. That means you know exactly the goal function, you know exactly the decision function, even if it's not optimal, at least you need to know one of them, and you know the PDF of what you want to quantize. Not for the clustering case, but for the continuous case. So what can we say? If you want to relax the knowledge of F, we have looked at this problem a bit by using very simple forward neural network, by using a couple of hidden layers and something like 20 or 30 nodes. and then you have applied this thing. Okay, but you can improve it largely what we did, but that would be a first extension of this work. Okay, using machine learning to relax the knowledge of the goal function. And when you have only access to the realizations of F. Second thing is, okay, now you don't know the optimal decision. And you also want to learn the decision function. We did nothing. We did nothing at all for this problem. When you don't know phi, okay, then you have seen that this can be handled with, and we have made the first step towards this direction with clustering, because for clustering you don't know phi, just use data, and you are still able to adapt the approach. And then there is strong assumption, and I insist because it is very important takeaway message of our study. We consider the case where everything is smooth. Everything is smooth. Okay, you have second derivative. You have seen you can differentiate as much as you want, but we have not performed the analysis for the non-smooth case. That would mean this function has jumps, for instance, or same story. The decision function has some jumps, which is very interesting. Okay, we have not explored this, and in fact, this sounds maybe crazy, but the most interesting case. Okay, remember these huge gains. Okay, let me do it in a more, say, smarter way. You remember these gains? For instance, here you have by moving from ear to ear, you have a huge compression rate. Okay, but in fact, this type of decision is typically non-smooth. So that means that's an intuition. This is not a proof. But if you want to have very large gains for this goal-oriented approach, in fact, you need to consider the non-smooth case. And this is where we have the largest gains. Okay, we have seen, okay, it's possible to have large gains here, but for some metrics, like the LP norm. But for more regular metrics, you have some gains. They are interesting, okay, but they are not, say, sometimes not always super large. They are significant, okay, but not always super large. So if you want to have super large gains, definitely you need to extend all what we did for this non-smooth case, okay? And you need to work with this semi-continuous functions, not differentiable, and okay, this framework, okay? And then that would be very nice to revisit the two problems you have seen, finding good quantizers and defining the classes of functions for which a prime is hard or not. Okay, so Maxime, that would be it for the presentation, and I would be very happy to have questions and try to answer them.
Yeah, great. Thank you very much, Samson. And yeah, we have some questions. So one question which I see in the chat is actually can only, so I think it's about telecom. So can A laws and mu laws be derived by the framework you present?
Yes, exactly. Yes, that's a very good example. The mu law, okay, this logarithmic law, in fact, it is inspired from what you get. Okay, let's go here. If you specialize our analysis, okay, to this function, okay, then you have the convolutional paradigm, okay. So if you look at the convolutional paradigm, then you will have exactly this. If the distribution, for instance, you consider voice, okay, and this is what people did a long time ago. They say, okay, the probability of shouting is low, the probability of whispering is low, so let's derive some logarithmic law. But it's exactly this. The logarithmic law, okay, represents the density of what you're going to compress. Okay, so that's a good comment. It can be found from this framework by specializing it. Yes.
Okay, great. Thank you very much. Yeah, I have also a question from my side. Yeah, if you speak about like machine learning more, then the problem of quantization which appears there, which is of a very different nature, is when you have, for example, a big network, right? And you want to save space and probably inference time by quantizing the network. So you have some weights and then you quantize them. And then you probably can be different variants. You can optimize afterwards, or you already have a trained network and quantized after that. So I understand the formulation is very different from what you consider. But did you think about that problems? Probably some mathematical rigor can be added for such types of problems.
Yes. So I don't know if I really get what is behind the question, but if I get it, for me, I see it like this. So you have a network, say, with weights and biases, and of course, one question is, could I make this network smaller? Because if you take too many nodes, it's more complex, etc. So could I get some abstraction? So I have a network, and could I get some abstraction? That means a smaller network which gives almost the same performance. So if this is the question, and then you would like to quantize all these weights and biases, yes, you have a vector quantization problem. That's true. I have thought about this. But then, to be honest, it is a very large dimension problem, okay? And the algorithms you have derived, they work in the vector case, but they are not scalable. They work for dimensions, say, 10, 20, 30, okay? They work. The clustering algorithm, for instance, it works quite well, but not for large dimension. Say, for more than 100, our algorithms, they don't scale, okay, in terms of complexity. But for the problem mentioned by this researcher, you will have a lot. You have many nodes, so the dimension of the problem is huge. So I think the challenge is then to be able to derive a low complexity quantization algorithm. But then, if you are able to do that, of course, you would be able to abstract a large NN, for instance, to a smaller NN, by using this framework, okay, which would need to be extended by far. But the approach, the same idea, can be used for that, yeah, to do some abstraction. Yeah.
Yeah, great. I think it's a very insightful answer. And yeah, I have one more question. You consider this clustering problem, but also the other related problem is graph clustering or community detection. Did you consider some application to finding clusters in graphs?
I've thought about this also, but no, I didn't do anything. I didn't do anything in this direction, but
because I think that goal-oriented something like it's really interesting idea, and I even have seen some papers recently in machine learning in different applications where people try to do like not what you do, but in the same direction, like trying to figure out exact functional you want to optimize, and they also call it goal-oriented something. Yeah, and I think that also for community detection, it might be also very relevant. Just you need to find the right applications where it's indeed needed. Not that many graph data sets available, but probably something related to, again, energy transition, I don't know, energy network, something like that might work. Yeah, that's very, very interesting, I think. Okay. Yeah, I don't see more questions in the chat, so I think we are done. And thank you very much for the very interesting presentation. And we actually have we had a lot of people, but in among attendees, but probably not that many questions. Probably everything was clear.
Yes. Okay. Thanks. Okay.
Yeah.
So thanks to everyone. So of course, I will send you my slides if you want to use them. And for researchers who are interested, just email me and I can give you the resources you want. Okay, we don't put them on the web because these are papers under review, but for point-to-point, say, exchange, it's okay. We can give them to you. Yes.
Yeah, thank you very much. And I'm sure some colleagues will contact you if they're interested. Okay, thanks a lot again.
Okay.
And yeah, thanks for coming to our seminar.